Hi, welcome to the ZP Developer Zone. So we like to do this Developer Zone once a week, and it's really just answering technical questions that have come in during the week. So today's the 28th of July 2024, and I'm doing a quick run through of about 6 questions today. Question number 1 is about chloride sensors, so I will answer the questions. Somebody else is making a lipase or lipase sensing system. I strongly suspect that they're using oxidase enzymes because it finishes in hydrogen peroxide. So I will talk about how to detect that hydrogen peroxide. Question number 3 is quite a lot of questions here. Somebody wants us to make 10,000 SPE Pyrene NHS sensors. I think realistically you have to do the first work on this for ZP to take on such a large. It's not even a large volume actually, but to take this on. You have to do the research. ZP can later on manufacture, but you have to do the research. Can DNA monolayers be made on Pyrene NHS? I believe so, but you have to do the research. The thing with, I think, chemistry and biology is because it's not deterministic like engineering. What I mean by that is, in engineering, if I wanted to make something like this, I can make it. But if I actually want to make a particular molecule, my effort doesn't equal reward. So unfortunately, in like the wet sciences, chemistry, biology, you have to do it. Somebody can give you an opinion, but you have to do it. So unfortunately, I can give you an opinion and I think it would be fine, but you genuinely have to do it because there's always something. There's always a nuance that you have to overcome. That's the joy of being a scientist, either in the chemistry or sort of biology domains. We do have a facility to do automatic drop casting. I may even have a video for you on that. If you're going to be at some point shipping 1 million sensors, by the time ZP is shipping 1 million sensors, in our labs and in our testing, we will have easily tested over 10 million sensors. So just understand that if you were one day going to make 1 million sensors and you wanted them to be good, you will have easily tested over 10 million in the R&D part of the program. Just out of interest, I do have videos on YouTube, and you can find them on Google. I think these videos are kind of titled "What's the cost to get to market in IVD and in vitro diagnostics? What's the true cost to get to market in IVD?" from Zimmer and Peacock. And there I'll talk about the history actually of companies. It's easy to say that most companies easily have raised over 50 million US dollars in the IVD, in the in vitro diagnostic space, by the time they actually get an in vitro diagnostic to market. Now with ZP it's a lot more efficient, but just have that in mind. And if you're looking for those quite deep videos on that, you Google Zimmer and Peacock, what's the true cost to get to market. I think that will hopefully help you find them. You can get a quote on our portable cloud potentiostats. I have links to the cost, so as long as you're happy with the cost, you can have a quote. Just out of interest, they're referencing here a third-party potentiostat. The third-party potentiostat that you're referencing is not cloud enabled. It does plug in and work with apps, but it is not cloud enabled. What the potentiostat that we're discussing is able to do, so when I say the potentiostat, maybe I should just change screens for a second. This potentiostat is in Bluetooth connection with my phone. My phone therefore gives me connectivity of the data that this potentiostat gathers, and I can send it up to the cloud. I will do a demonstration of this at the very end of this. In question number 6, where somebody's asking about hepatitis B, I will do a demonstration on this, so you will see that. The potentiostats that you're referring to, sure, they either plug into the phone by the USB-C, or maybe they make Bluetooth connection. But what we are doing at Zimmer Peacock is taking the data, processing the data, running a calibration routine on the data, and sending a concentration back to the phone. That is the data stream. So most potentiostats, including the one that you are referring to, only generate data. ZP is the only potentiostat that's cloud enabled that has the data stream. Collect the data, process the data, extract the signal, put the signal through a calibration routine, get a number, the number comes back to the phone. ZP is the only potentiostat, or this sensor or potentiostat is the only one that does that. Sorry, blank. So there isn't a comparison. So be very, very careful with trying to make a comparison. It generally doesn't. Now, if you're a bit confused about that, I have personally invited you to a couple of webinars. We've got the Sense It All webinar that I'm coming up soon, and I also have the academic webinar as well. So please come to the webinars, because I did notice you didn't come to the last webinar. Did you ever work or come across DNA that could be used on SPEs with high storage stability? This has been done before. This has already been done. You will find this kind of technology in the products of a company called Genmark DX. Zim and Peacock does this. So the quick answer is yes. Doesn't mean that you can't have to go through the pain as well. Everyone has to go through the pain. Your DNA, your formulations, these will all be different. You will have to go through the pain. You will also have to do what's called accelerated shelf life studies. Accelerated shelf life studies. You will have to do them. You can't avoid, unfortunately, the steps of making a robust product are long and expensive. You just can't avoid them, unfortunately. You are aiming to make a glucometer for infectious diseases, and the SPEs. May I show you that you can do this? The glucometer, let's say for infectious diseases, if I just do this exists. This will do exactly what you want. If you start using ZP technology and you develop on this potentiostat, you will be able to make that claim that you have a glucometer for infectious diseases. In fact, one of the questioners in a minute on sodium, I'll be doing a demonstration later on using this technology, and you'll see how little volume the electrochemical sensors actually require. So your vision, it is technology possible today. Most of the effort that you're going to have to put in is actually functionalizing electrodes like this, making that functionalization robust, checking the shelf life. These are hard things, and unfortunately, you know, somebody has to go in the lab and do it. Now, I think that person who goes into the lab and does it is actually you and your team, because I think that research is best done at universities and development is done well in companies. But the fundamental research here, I'm not sure has really taken place. Somebody else is interested in our wafer holder for, and by the way, I'll jump into question number 3 in more detail. I've got some more slides on this. Question number 3. Somebody's interested in what we call our wafer holder. They were kind of like, well, how do you get the voltage and current into that wafer holder? It does have cables. I will bring up some images on that. I know that the video doesn't show that online. The guys made the video and they didn't show the electrical connection. I know that. It's just, I haven't got them to make a second video yet. Number 5, somebody was looking for some sodium sensors. We have obviously at ZP, I think sodium sensors is probably one of the longest, let's say, products that we've had. They're interested in the I-stat runs between 100 and 180 millimolar. That's because homeostasis of sodium in the human body is about 135 millimolar. So that's why the I-stat has that range. They don't need, I mean, the body's very good at actually holding its sodium range. Hence, you know, they don't need to have a massive range. They say millimolar, milliequivalents, it's fine. The detection limit, just out of interest, you'll see it in a minute, that we're easily detecting 40 millimolar, for example. Easily detecting 40 millimolar. Our detection range is probably much greater than actually you'll generally require for your application. And you're also interested in continuous measurement. If you have to look at our raw data and determine whether the signal is stable enough for your application. I don't believe, actually, I can think of companies who are doing continuous measurement of sodium. I'm not sure that they're necessarily super commercially successful. Can you use it directly with bodily fluids? You probably can, but you have to try it. I can't show you confidential data on our sensor in various bodily fluids. I think the bodily fluid that you're most interested in is interstitial fluid. This is probably the easiest bodily fluid. It's essentially filtered. So blood, is full of a lot more things like red blood cells, for example, hemoglobin. But when you get to interstitial fluid, it is a much cleaner, is a relative term. It's a cleaner sample than blood. So I think interstitial fluid is fine, but you still have to do that work. What types of fluids have this been tested on? Well, we've tested it on blood, we've tested it on sweat, we've also tested on interstitial fluid as well. But you have to test it. It has to be, your system is your system. What we've done in the past is what we've done in our past on different systems. If you're building a new system, then you have to do it. The difference between our standard and our chloride resistant version is that in some applications, not interstitial fluids, but in some applications, chloride can be quite variable. Seawater would be an example. So sometimes we fix the chloride concentration. I would generally advise you to actually just go for the standard sodium sensor. Don't get the chloride resilience sensor yet. The chloride resilient technology really needs to be tuned for each application. The reason being is we try to hold a reservoir of chloride, but if we're going to create that reservoir of chloride, we'd rather make that reservoir of chloride similar in concentration to the final clinical application. That way then we don't have much diffusion of chloride in and out. So I would actually go for the standard sodium one, not the chloride resilient one. Honestly, I always try, I'm going to say it a few times today, I would rather people went simple and then builds up complexity. If you jump into complexity, you just get confused. How resilient is it against chloride? I don't have any data to share with you on that. This is our raw data. This will give you, this will come up again later on. But if I'm looking at my data about 160 millimolar, I can see once it starts plateauing and it's actually getting some quite nice stability about it. So if you're going to do continuous measurement, it's really stability that you're going to have to think about most. But with ZP, we put the data out on the web store. If it's convincing enough, that's great. If it's not, then you do have to find technologies elsewhere. Question number 6. Somebody wants to make a hepatitis B sensor. They're asking us for a biosensor and receptor. All I can advise you is how to do it. You will have to do this. I will say one thing. You say here, I want a gold, platinum, and one other metal. The reason that people want gold, platinum, and one other metal is because they're either read a scientific paper where they had like a gold disc electrode and a platinum and gauze electrode and a silver chloride reference electrode. And now they think it's only those three that combination of those three that will then work on an SPE. Do not make a technology based on gold, platinum, and one other metal. Do not do that, because you're now going to have gold, which is very expensive, and platinum put down, which is also expensive, put down in 2 processes. I mean, most screen printed electrodes are made, the working encounter of the same material, and then you've got silver chloride. Why is that? Because then it's to print the working encounter is one material, it's done at one time. That's, so it's one material, one process. Once you've asked for gold and platinum, that's 2 materials, 2 processes. You're building in cost. You don't need to do that. It's amazing. I've had to sort of have conversations with people, why is it you want a platinum electrode often? And it's like, well, because when we were doing the lab work, it's because we used platinum gauze. Right, okay, that's not a good reason to then want to migrate that into your actual product. I think as different people, we're a little bit different. Honestly, if you hear the passion in my voice, it's because I'm genuinely trying to help people get to market, and avoiding errors now will save a lot of money later on. So that's why it's nice. I do appreciate people asking us in these webinars, because we can kind of head people off, let's say. First of all, if you're wanting to commercialize any point of care device, whether it's hepatitis B, whether it's DNA based system for applications, let's say in Pakistan, please come to this webinar. I do check to see who's registered and who's coming. Please come to these webinars. This is where we talk about commercialization. So here's commercialization. Please come. Wearable webinars. If you're interested in if you're just interested in basically measuring things in a wearable biosensor, do come to the webinar here. It's next week. It'll just give you a lot of insight into what's happening today and what's happened in the past and how to avoid errors of the past, let's say. If you're in academia and you're looking to translate technology from your lab and actually have some impact and get it onto the market, please come to this webinar. We put a lot of effort into these webinars. We do good demonstrations. We talk about philosophy. We talk about strategy. Please come to them. I can't cover them in enough detail, some of the material that I do need to get across in answering these questions 1 to 6. So I would even, so please come to these webinars. Somebody's just interested in our chloride sensor. It's got a range of 0.25 millimolar to 1000 millimolar. And the data's up on the website, showing the kind of change in signal versus chloride. I would say with this, if you're going to buy that chloride sensor off us, please make sure you get these connectors off us. If you've got a large potentiostat from a company, I think that manufactures them. Well, these days they're in Switzerland. They've got 4mm banana plugs. Get this connector. If you're using a smaller potentiostat with 2mm banana plugs from a company in the Netherlands, for example, use this connector. I'll put these links underneath the video. So we do have a chloride sensor. There's data up on the website. If it's interesting, please get them. But please make sure you get the connectors as well. And check the instrument that you're using, which connector you'll actually need. Generally, people only need 4 or 2mm connector, but please check the potentials. Please check. Question number 2, lipase sensing. I know I'm being a bit naughty here. I'm using my glucose slide here, but somebody's made, and this sounds really quite interesting actually. They've made an enzyme formulation. I used to call them an enzyme cascade. So you've got in fact, I've got the slides here anyway. So this sounds really good. It sounds like it's really compatible with the kind of things that we like to do at ZP. It sounds like you've got some sort of formulation. It doesn't have to be necessarily in a polymer. You can drop cast these kind of things onto glucose sensors. I realize as I'm saying that, I'm opening up a can of worms and more questions. But if we're making what's called a continuous glucose monitor, we would do it this way. But if I was making what I call a discrete test, and I will do a discrete test at the end of this webinar, so you can watch me do a discrete test, and we would build up our peroxidase enzyme system this way. You would have lipases, we have glucose, but it all works the same way. The reason I bring this up is because when you generate that hydrogen peroxide, you can detect that on a platinum electrode versus platinum electrode poised at 650 millivolts versus silver chloride. You can do that. I mean, I do have a potentiostat that could do this. In fact, here it is here. I wish you that you would use it. You may already have potentiostats. I can also appreciate that. Now, so platinum is your first guy. I can understand your question. You're actually asking, well, what catalytic materials can I use? And you can use, for example, in fact, here's some of our screen printed electrodes. So I do recommend the platinum. I probably recommend the platinum 501 because it's got a circular electrode. It's very easy to pipette onto, so the platinum 501s. You will notice that the platinums are expensive. Now, you can get around platinum's expense. The cost of, if you've ever got a choice in life, and this does also talk to the hepatitis B people, if you've got a choice in life, don't go for platinum. If you ever want to make a low-cost sensor, think about it, it's platinum. Don't go for gold if you ever want to make a low-cost sensor. Think about it, it's gold. Unfortunately, it has to be carbon. In this particular case, this person's making a sensor that ends in hydroperoxide. So I can understand that platinum would be, if I'm going to, I have to crawl, walk, run. My crawl step is you're going to just do it on platinum electrodes in the R&D phase. Get a certainty that everything is working. So, here's a link to the platinum electrodes that I recommend. We do have Prussian blue electrodes. So Prussian blue will work with hydrogen peroxide. We do have them. They're expensive because we have to do extra fabrication. Be really, really careful, the questioner here. You will find Prussian blue sensors or Prussian blue formulated inks on the market. Please, I don't think they work particularly well. I've had clients who've used these inks which they've got cobalt in them, or they've got something like Prussian blue. Honestly, there's so little cobalt or Prussian blue in there, I think they actually don't work really well. These will work really well, but I just feel like actually what I would recommend you is you start with platinum, get the platinum working. Then you could think to yourself, really, I can't really commercialize platinum, it's too expensive. You could try then some of our Prussian blue ones just to make sure that that kind of system is working. But I appreciate ours are, expensive. What I would actually suggest you do is you get then some of our 501 carbons, which you find are lower cost. Get some of our 501 carbons and then put a Prussian blue layer on top of that. Honestly, there will be thousands of papers on how to put Prussian blue on top of carbon. Thousands of papers about it. Start off with platinum, get it working on platinum, then know that you really do want to take the cost out of platinum. Platinum is a killer. People have to generally have a strategy in life. Your strategy, anyone who's listening to this day, please try and avoid gold and platinum. Just think about them. Platinums are very valuable. Industrial materials are great catalyst. That's great. There's lots of people who want to use platinum. Think about gold. Gold is a nice inert material. Engineering, science loves it. And so does gold investors. So you're competing against a lot of people for gold. Carbon, carbon is what you call a commodity. The commodity means you can buy it from lots of places, and in the end, it's the lowest price always wins out. Please go for carbon. So with this particular case, I can understand that carbon and hydrogen peroxide are very good. You can't oxidize hydrogen peroxide very readily on carbon, but if you give it a layer of Prussian blue, you will find thousands of papers on how to make a Prussian blue layer. That's the direction I think you should go in. The equipment that you'll need, please use our screen printed electrodes, the 501 platinum and the 501 carbon, but you will need these connectors. You have to check your potential stat, see what banana plugs your potential stat has. I suspect they're 2mm or 4mm, and get the connector accordingly. Question number 3, this is a good one. This is a really tough one actually. So I love the ambition of the 1 million sensors. So somebody has an ambition to make 1 million sensors. I've actually got this video here. This is just to say that ZP, if we're doing deposition on sensors, we are using robots. In the end, you can't make, say 10,000, even 1,000. You can't make 1,000 sensors repeatably without robotics. I get it. It's a tough one. At ZP, we do have robots that basically do this for us. We can offer it as a service, but we cannot offer this as a service necessary to academic groups. It's too expensive. Programs, when Zimmer Peacock is involved in a program, we do contract development, contract manufacturing for companies. We're doing programs that are in the hundreds of thousands of US dollars per month. Not because it's just the cost and the team size that's required. So with academia, I would generally say please do as much of the work as you possibly can. Now I would ask you to please use our materials, and when I say use our materials, you can get potential stats from Zimmer Peacock. These are really good potential stats. These are, if I was trying to make a glucose meter type system for hepatitis B, that's as close to that as you can get. It is cloud enabled. These are really reproducible screen printed electrodes, but you have to do as much research as possible so it's as robust as possible before you can really start talking to companies like Zimmer Peacock about contract development on this kind of work. But we do have the robots for this kind of work, and in the end, yes, you're never really going to get the repeatability that you require until you necessarily go robotic. The problem about buying robots like this is, when I say like this, I should go back to my screen. Problem with buying robots like this is not just about buying the robot. You have to run this robot over years and years. These are high maintenance equipment. So it's not just the purchasing that's a problem. It's also the operation of these kind of robots as well. So I know people go out and buy robots like this, and then a year later they're gathering dust because you know, a piece breaks on it. A piece on this can cost 2,000 euros just to replace. Be really careful about getting into the game of buying robots. If you do the hard work on the research and you do your shelf life studies, then you'll be able to answer the question whether you can store them for 1 year. There is precedence for people doing this for 1 year. ZP is one of those. But see, you have to develop that formulation. Then you have to do accelerated shelf life studies. You have to answer this question. I can give you some certainty that it's possible. I even know that companies that are doing it commercially. Just Google Genmark DX. They're owned by Roche these days. They do this commercially, but you still have to do the work. The third-party potentiostat that you're referring to, it's truly only collects data. At Zimmer-Peacock, we collect the data, we transfer the data to the cloud, we smooth the data, we find the signal within the raw signal. We put that signal through a calibration. We turn that calibration into a number, with units, and we send the number back to the phone. That's not done by any other potentiostat. This is a unique type of potentiostat. We have done this in the past. DNA. If you're looking for commercial examples of DNA-based sensors, go and look at Genmark DX. And yes, the potentiostat that you want, or rather you want to make a glucose meter for infectious diseases, absolutely. I completely get it. This is exactly why we've built potentiostats like this. This is the nicest kind of potentiostat in the world for people who will have that dream. And it's really nice because what's wrong with a lot of potentiostats is they have slots in them. The problem with slots is when you slot a screen printed electrode, there's this little gap and liquid gets in there, and that liquid gets in there, that potentiostat is dead. So this is quite a robust little potentiostat for applications like that. If the prices look good, these can be purchased off the web store, or then quotes can come out. But I do want people to understand the price before asking for quotes. I think if you're trying to do a hepatitis B sensor, the real work that you need to, well, first of all, assays. At ZP, with our screen printed electrodes, we've really worked on repeatability. So at least the foundation of building an assay for things like hepatitis B is solid or good. The problem with a lot of screen printed electrodes, I know that this particular person's used some screen printed electrodes, for example, from Spain, and they've also used them from, I think it's Taiwan, and they have a problem. And the problem they have is actually repeatability. At ZP, we're completely aware of this repeatability problem. Please come to our webinar for academics, which I think is on the 7th of August. Please come. This is a personal invitation. And there we'll talk a lot about repeatability of screen printed electrodes. And actually, the lack of reproducibility in manufacturing screen printed electrodes is actually what's holding back most academic research. With ZP, I would recommend the 501 for you. You only have to work on the working electrode. Figure out the assay. Figure out the method that you're going to do. I suspect you'll end up doing either impedance spectroscopy or square wave voltammetry. Figure out the calibration routine, because actually we can program that then straight into the potentiostat, but you need to do the work. You need an assay, you need a method, and you need a calibration. When you've done that, then you're starting to come out of the research and get towards the development, but you really need to get through these processes first. I've just left question number 3, but question number 3, I'm going to do some work on question number 6 at the end of this, so hang on for question number 6 as well. Question number 4 is much easier. We do have a wafer holder so that people can do electronic or electrochemical processes at wafer level. Obviously, to do that, you need to bring a voltage in or bring a current in. I'm sorry that the video that we put online didn't show that. We do actually have a cabling system, so you can bring in. These cables are quite thick because we're actually bringing quite a lot of current as well. So if you're interested, this can be found in this URL here. Question number 5. I'm going to probably dive back into, maybe I'll say something slightly different second time round. The questions are, so somebody probably wants to make an interstitial fluid sodium sensor. There is a product out there called iStat. The iStat started life in 1984. Just out of interest, I do have a video and material online sort of saying what is the cost to get to market. So if you ever Google maybe what is the cost to get to market, and Zimmer and Peacock. Hopefully you'll find that material, because I do talk about the iStat in that and show you that, you know, how much money they spent. Now the iStat spent a lot of money getting to market because actually they did have a lot of analyte as well. But just to say, I do understand the iStat. I do talk about it online. You can find some useful supporting information there. We have no problems with your clinical range. The clinical, you know, the data here is 40, 80, 160, 320. The range of the sodium sensor from Zimmer and Peacock is far in excess of what you'll actually need. Your limit of detection, there's no way that what you need, you know, your limit, let's say iStat was trying to do 100 millimoles, 100 millim, yeah, I should say moles, I should say millimolar. 100 millimolar, you know, you can easily see that we've got signal outside of that range, and we've got strong signal as well. If you can see a signal by eye, then, you know, it's clearly a strong signal. You will be interested in its stability. The data that we have online is the data that we have online, and you will have to characterize that. I'm actually playing a video here because I realized in that video they actually even show you how to do the experiment, or how to do a stability experiment. So you can find that video also in that link as well. We have tested them in different various fluids, but the business model of Zimmer Peacock is we'll put stuff on our website and people can choose to adopt it. We generally do that for the kind of academic community. We're doing a lot of work actually that's never seen, you know, that's done with companies. And if we've done it with companies, then we're not going to discuss it or show any data. I would honestly argue that you need to almost repeat the experiment that I'm showing in this video here. Before you start getting into complexity, you need to get what's called TRL3, that you've done a proof of principle on technology readiness level number 3, that is, that you've proven something works on the bench. Do the bench experiment that actually that video shows. When you've done that, it's time to start asking about resilient electrodes, etc. Question number 6. I'm wondering if question number 3 and question number 6 are actually same people from different groups. First thing to say, I know I've said it already, you do not require gold and platinum on a screen printed electrode. Honestly, that is just loading up processes and cost onto the product. If you want to make a low cost, the reason I think that you're asking that is because I think the way either the papers or the experiments you've already done are kind of done in this kind of vessel where you've got like a gold disc electrode, a platinum gauze, and a lab silver chloride reference electrode. You're using quite large potentiostats and probably a PC, where we can do all of that work these days on something a lot more, you know, elegant. I will do a quick demonstration of this shortly. So this will the reason I've got all this running here will become apparent shortly. So the problem I have with the left hand side is it really holds well. It's interesting in this case, see, because when somebody's asking for gold and platinum, it sort of tells me about the kind of experiment or the kind of papers they're reading. See, so it then that sort of, oh well, I need a gold and platinum electrode, then tries to pass all the way into, now how do we make a commercial product out of this? And the fact that gold and platinum were used in that lab experiment then tries to translate itself onto but next what they want to do is make a low cost sensor. Of course, the words gold and platinum do not translate well into low cost. The questioner number 3 already knows this, so I apologize for the rapidity. But if you're looking for a strategy to make a low cost, essentially what this person's trying to do is make an immunosensor. If you have a strategy for making a low cost immunosensor, please read this paper. It's not open source, but it's free. I'll put a link underneath the video. I would say I've got the picture of our hypervalue carbon electrode here. I actually think you need to use our carbon 501 screen printed electrode. It's easier to pipette onto. This I know this is the same binding chemistry that I suggested for question number 3. This is Pyrene NHS. Pyrene NHS is a good molecule for coupling, let's say, receptors, antibodies, DNA, aptamers to a carbon surface. Then you can couple the material. Then you have to block that electrode, and then we follow this kind of functionalization using a technique called cyclophotometry. This potentiostat is perfectly capable of doing cyclophotometry. And then you can actually do the testing. This is using a Faradaic, I should say, it's got a reporting molecule in it. We're using ferricyanide in this particular case. Now here we actually used differential pulse voltammetry. These days I'd actually recommend square wave voltammetry. This paper came out possibly 2018. Today is, check myself, 2024. I was thinking we'd, anyway, it's 6 years later. So we've learned a lot in those 6 years. And that's the nice thing about science, isn't it? It's not very static. So I would actually recommend square wave voltammetry these days. Differential pulse voltammetry and square wave voltammetry are pretty equivalent, I would suggest. I just feel like, there's a bit of a more people doing square wave voltammetry. There's therefore more literature on which to rely on when doing square wave voltammetry. So my suggestion is square wave voltammetry to get going. Here's the carbon electrodes and here's the potentiostat. Sorry about that. I've actually got myself, I'm going to do a quick demonstration in a minute, but I really want to emphasize that when I do a demonstration on this potentiostat, this is a cloud-enabled potentiostat. I know that question number 3 was like, well, there's other ones. They're not. They may, even if they send the data to the cloud, this is an entire data pipeline. Raw signal to the cloud, signal is processed, signal. Then we get the information out of that signal. What is, for example, is it the peak height, etc. And we convert that then into that kind of concentration and give back the final user, not cycle voltammetry or square wave voltammetry or impedance spectroscopy. We give them back the number. That's really a different workflow. If you haven't to follow anything I'm doing here today, you can actually register on Julie. Julie is a cloud system. When you register on Julie, you'll register using your email and you'll create a password. So later on, if you decide to put the Sense It All app, so when I say the Sense It All app, this is the Sense It All potentiostat. This is the Sense It All app. If you decide to install the Sense It All app on your phone, make sure that you log in using your Julie credentials, because then Julie and that app are basically they're synchronous. What you gather with the app will go to Julie. Only if you then log into the app using your Julie credentials. So create a Julie account, your email, and create a password. Use that email and that password to log into the Sense It All app. The next question is, where do you get the Sense It All app from? You can get it from the Google Play Store if you're using an Android, or you can get it from the Apple App Store if you're using a Apple. Of course, this is recorded, so you can pause at this point. You can scan these QR codes. So I've got the app up here. What I'll do now is I'll just scan square wave voltammetry, for example. Now, this is square wave voltammetry, or the app is square wave voltammetry. What does that mean? That means I'm just going to go to here. It actually says something here. It actually says device connected. What that means is this app is ready to do square wave voltammetry. It's in Bluetooth connection with this. This is now, when I go to assay, this will actually make this run square wave voltammetry. I can just go to EIS as well, which is not a bad technique. Here is EIS. Okay, so we can just go to different techniques using EIS. You can try that out for yourself by scanning these QR codes. But open a Julie account. It's free to open. Use your email, create a password, then download the Sense It All app to your smartphone. Log in using your email and password. Examples, and this is the bit. Then I'll give you an example in a minute. What this says, see, each one of these then shows that for each one of these analytes, we're actually running an electrochemical experiment. But let's say real people, let's say clinicians in Pakistan who want to look at hepatitis B, they do not want to see your raw data. This is the power of this Sense It All potentiostat, that actually you can make it analyte specific. So in fact, what comes to the client or the final user is the concentration of that analyte, not the sort of whole raw signal. As I say here, this is to remind me to do a demonstration. I will do a quick demonstration. So yeah, I'll do a quick demonstration. Let me take this sensor out for a start. On the screen is electrode. The only reason I'm taking this out is to kind of give you a sense of, actually, this is a really clever little potentiostat. most potentiostats that nobody's even designed them or even thought about how you're going to actually clean them. But let's say something got spilt on this, which actually I can see something gets spilt on this. I can take this apart. It's much easier to clean at this point. I click that back in. It's magnetic. I can, that's all fine. You never need to take that out really, but it's just to show. Now I'm going to put the sensor in here. No slot, right? No fiddling around. Click that up. It's now made electrical contact. Now I'm going to put the sample on here. Actually, that person in question number, the sodium question, was asking what's the minimum sample. Yeah, that's a good point actually. The minimum sample, a glucose strip, by the way, has a minimum sample requirement of about 300 nanoliters. 300 nanoliters is ridiculous. This is 50 microliters, by the way. But if you make a microfluidic chamber, you can make that much smaller. We often work with like 4 microliters at Zimmer and Peacock. Anyway, that's 50 microliters that I put on there. I'm just going to give this a quick name, which I will do now. Tab 1. That's fine. I'll go to assay, start measurement. Okay. So this is a potentiostat. It's actually doing cyclovoltammetry. The only reason I'm not showing you cyclovoltammetry is because I'm also showing you that real people in the real world do not want to see our cyclovoltammetry because, in fact, it will just end up essentially confusing them. But this potentiostat, I mean, it's really thinking about the end user. This is flashing a little light here, and so it tells it's helping me as a non-expert, to actually run this potentiostat. Now I'll also show you a couple of. I'll change my screen just real quick. How do I do that? I do it by this. Right, it's giving me a result, micromolar, and it says upload complete. So this is truly sent that data immediately to the cloud. It's not just phone enabled, it sent the data to the cloud. Please come to our academic webinar and please come to our Sense It All webinars. Those will be linked underneath this video. I'm just going to share my screen quickly. Here's the data. This is really important. If you're trying to do, let's say you had 1 million sensors that were going out to people that are being used by clinicians, you definitely want to have some vision on that raw signal. This system, what this system has done is this. I've got the raw signal, great, but clinicians don't care about the raw signal. But what I have here is a toolbox, and in my toolbox I've said, take the second scan. I've said put it through what's called a low pass filter. So I can, I've got tens of filters of, at least more than 10, probably about 15 or 20 here, filters available to you. You may not need that filter. Your data may be super clean, but of course, if you're going to get data in the real world, you can end up with noise in the signal. I've said to it, flip the y-axis. I've said to it, show extracted values. I've said, analyze the peak height. Analyze the peak height in this particular window. Fit it to this formula. Understand, see what's happening here is we're processing it, the data. We're then telling it to look for, let's say, the peak height. We told it where to look for the peak height. And we've said, when you found that peak height, can you fit it to this formula, please? Because when you've done all that, what does that mean? It means it actually processes the signal to the concentration. And it's the concentration that the end user gets. That's the big difference. That actually we've got, this is called a data pipeline. There's a data pipeline intrinsically built into this. So genuinely, there isn't another potentiostat on the market like this today, which I am super happy about. So that was the demonstration. I'll do a bit of a, so ZP chloride sensors, we do have the data on the website. I have advice on connectors. I hope you go forward with that. With your lipase sensor, I generally say start with a platinum 501. If you can get some signal out of it, not out, the 501s work perfectly fine. It's whether your assay is completely as good as you hope. But once you've got through the kind of platinum barrier, then I would actually say think about the carbon electrode and think about mediating it with Prussian blue. Question number 3. You will have to do this piece of research. You will have to take that Pyrene NHS and you will have to put your DNA onto that. You have to do that. Otherwise, I'm trying to give you certainty in the world of science. And the world of science, when you're talking about atoms, molecules, You really need to, sometimes, you can always have a strong opinion, but you have to do the science. We do have robots that do this kind of work, but I think eventually you want to make 1 million sensors. The first question is, have you made one? Then have you made 10? Then have you made 100? Then have you made 1,000? Then it's, have you made 10,000? Have you made 100,000? Then you're starting to get towards making 1 million. There's a long road to go yet. So, but unfortunately, the first step in any long road is the first step. So you do have to start taking the first step. Please check out the pricing. If the pricing is fine, then we'll do you a quote for it. Genmark DX is a company you really need to look at regards to this. Question number 4. Yeah, sorry about the video online, but actually that wafer holder does have the ability to bring in current and voltage. The link that I'll put underneath this video will take you to the, let's say, the web page. You'll see there that there is cabling associated with this. Question number 5. In the end, you want to do interstitial fluid and you probably want to do continuous measurements. I would say get our sodium sensor, do the experiment that is shown in this video. That will teach you a lot. From there, you can start expanding complexity. Start off simple is my recommendation. Question number 6 is about hepatitis B. I've given you a paper. I'll put a link to that paper underneath this video. You will have to build that sensor. I don't believe, at least the biosensor, is not a commercial hepatitis B biosensor. Zimmer people is very capable of doing that, but we do that with large, well-funded companies or startup companies that are well-funded. These webinars and these answers are sort of intended for our academic colleagues. If you're in academia and you want a hepatitis B sensor, start buying the ZP potentiostats and screen printed electrodes, following the paper that I've recommended, and that will be the start of your journey towards hepatitis B. So thank you. If you've got any questions with ZP, don't hesitate to reach out to us. Okay, thanks very much.